Hello there, and welcome to the Sleepy Space Channel. Tonight, we travel to the edge of what we can almost reach to Alpha Centauri, the closest star system there is. It is a little over 4 light-years away, near enough to be called a neighbor, far enough to remain a world apart. 3 stars turn there together in the dark, a golden pair and a faint red companion, and among them drifts at least one rocky world, roughly the size of the Earth. This documentary will cross the long emptiness between the Sun and that system, study its 3 stars, survey its worlds, and ask the quiet question of whether the journey could ever truly be made. If you enjoy these gentle journeys, I invite you to like, subscribe, or share a thought below. It helps others find their way here, too. One sleepy soul at a time. But for now, there is nothing you need to do but settle in. Let your shoulders soften. Let your breathing slow. Allow your eyes to grow heavy. Let's begin. Part 1. Leaving the Sun behind. The journey to Alpha Centauri begins not with a departure, but with a fact. It is the nearest star system to our own, and it is still almost unimaginably far away. These 2 statements are both true at once, and holding them together is the first work this documentary asks of you. Alpha Centauri is the closest of all the stars, and yet the distance to it is so great that the human mind has no natural place to put it. The distance is just over 4 light-years. A light-year is the distance light travels in 1 year, and light is the fastest thing the universe contains. Nothing carries information or energy faster. And still, the light leaving Alpha Centauri tonight will travel for more than 4 years before it reaches the Earth. To look at that star is to look at light that began its journey more than 4 years ago. It is worth dwelling on the light year as a unit, because it is the unit in which this entire journey will be measured, and it is not an intuitive one. Light moves at a speed of nearly 300,000 kilometers in a single second. In 1 second, a beam of light could circle the Earth more than 7 times. In a little over a second, it crosses the gap between the Earth and the Moon. It takes about 8 minutes for light to travel from the Sun to the Earth, which means the sunlight, on any given afternoon, left the Sun 8 minutes before it arrived. Now take that same swift light and let it travel not for 8 minutes, but for a full year, and then for 4 years, and a little more. That is the distance to Alpha Centauri. It is a distance built from the fastest thing there is, multiplied by the patience of years. Expressed in kilometers, the gap is roughly 40 trillion. That number is too large to feel, so it helps to translate it into the scale of our own neighborhood. The Earth orbits the Sun at a distance astronomers call 1 astronomical unit. Alpha Centauri lies more than 260,000 of those units away. The entire span of our planetary system, from the Sun to its most distant planet, is only a few dozen astronomical units across. The journey to the nearest star is more than 10,000 times longer than the journey across everything we usually call home. There is a way of shrinking these numbers that makes the emptiness clearer rather than smaller. Imagine the Sun reduced to the size of a single grain of sand. On that scale, the Earth would be a speck too small to see, orbiting a few centimeters away. The whole solar system would be a region you could cover with your hand. And Alpha Centauri, on that same scale, would be another grain of sand, several kilometers distant, with nothing at all in the space between. That is the true proportion of things. Stars are small, and the gaps between them are vast. Try the same exercise at a different scale, and the lesson only deepens. Suppose the distance from the Earth to the Sun were shrunk to a single step, the length of one ordinary pace. On that scale, the outer edge of the planetary region would lie a few dozen steps away, a walk of a minute or two. And Alpha Centauri, the very nearest star, would be more than 40 kilometers distant, a journey of many hours on foot, with every step of it passing through complete emptiness. However the scale is chosen, the answer is the same. The space inside a planetary system is crowded with worlds. The space between the stars is not. This emptiness is the first and most important fact about interstellar space, and it shapes everything that follows. The distance between stars is not merely a little larger than the distance between planets. It is larger by a factor the imagination is not built to hold. Within a planetary system, worlds are neighbors, close enough that one can be seen from another as a disk, close enough that journeys between them can be measured in months and years. Between the stars, there is a silence with almost nothing in it, and the crossing of that silence is measured not in years, but in tens of thousands of them. That silence is not perfectly complete. The space between the Sun and Alpha Centauri is filled with an extraordinarily thin gas, a medium so sparse that it averages roughly 1 atom in every cubic centimeter. This is far emptier than any vacuum that can be produced in a laboratory on Earth. The best vacuum ever created by human hands still contains vastly more material than an equal volume of interstellar space. The medium between the stars is a near nothing, but it is not quite nothing. Astronomers call it the interstellar medium, and our solar system drifts through it slowly, carried along by the Sun's own motion through the galaxy. The interstellar medium is not uniform. It is gathered, in places, into thin clouds, and thinned, in other places, into great bubbles where the gas is hotter and even sparser. At present, the solar system is passing through a particular wisp of this gas, a faint cloud sometimes called the local interstellar cloud. The Sun entered this cloud long ago and will, in the far future, drift out the other side. Beyond that cloud lies a larger structure, a great bubble of hot, thin gas carved out long ago by the explosions of dying stars, their shock waves sweeping the region nearly clean. These features are diffuse and quiet, detectable only by careful instruments, and a traveler crossing the gap would never see them as anything solid. It is worth pausing on where the influence of the Sun itself ends, because the journey to Alpha Centauri does not begin at the orbit of the outermost planet. The Sun does more than shine. It also streams out a steady wind of charged particles in every direction, and that wind blows a great bubble in the surrounding interstellar gas. The bubble is enormous, reaching far beyond the planets, and its outer boundary is the true edge of the Sun's domain. Only when a traveler crossed that boundary would they truly leave the Sun's local territory and enter the open interstellar medium. Beyond it, the thin gas belongs not to the Sun, but to the galaxy. And even past that boundary, the Sun's gravity still reaches. Far, far beyond the planets, far beyond the edge of the Sun's wind, there is thought to lie a vast and distant shell of icy bodies, loosely held by the Sun's gravity, the remote source of many comets. This shell, if it exists as expected, extends an appreciable fraction of the way toward Alpha Centauri. In a sense, the very outermost reaches of our own system and the very outermost reaches of Alpha Centauri's may not be so impossibly far apart. The two systems do not touch, but the gulf between them, measured against the full extent of the Sun's gravitational reach, is not quite the perfect isolation it first appears. A traveler would still cross emptiness for the great majority of the way, but the emptiness has faint, distant edges on both sides. The point worth holding gently is this: the journey to the nearest star is, for almost its entire length, a journey through emptiness. And the emptiness is not an obstacle to the story. It is the story. There are no way stations between the Sun and Alpha Centauri. There are no islands, no rest, no landmarks. There is only the slow accumulation of distance, year after year of it, with the destination growing imperceptibly nearer and the origin growing imperceptibly more remote. Consider what the journey would look like in reverse, from the point of view of someone leaving the Sun behind. The Sun would not vanish suddenly. It would fade by slow degrees. For a long while it would still be the brightest thing in the sky, a disk shrinking gradually toward a point. And then, somewhere along the way, it would stop being a disk at all. It would become a star. A bright star, certainly, but a star, taking its place among the other points of light, no longer the center of anything. The change would be gradual enough that no single moment would mark it. There would be no instant at which the Sun ceased to be the Sun and became merely a star. The transformation would happen the way the transformation of a landscape happens to someone walking away from a city, the familiar shapes dwindling so slowly that only by looking back across a long interval could the change be seen at all. At some point, the traveler would look back and find that home had become a light among lights. From the halfway mark between here and Alpha Centauri, the Sun would appear as an ordinary, luminous star, sitting in the constellations of that region's sky, exactly as any other star sits in ours. This is one of the journey's quieter truths. The Sun is not special among stars. It is special to us because we live beside it. Seen from even a modest interstellar distance, it is one yellow star among hundreds of billions, distinguished only by the fact that it is ours. There is something steadying in that thought, rather than something diminishing. The Sun does not need to be remarkable among stars in order to be the center of everything that matters to us. Its ordinariness and its importance are not in conflict. It is an average star, and it is also the source of every warmth and every harvest and every blue sky there has ever been. The journey outward does not take that away. It only places it in proportion. The same will be true, in reverse, of the destination. Alpha Centauri, seen from Earth, is a famous and singular thing, the nearest star, the subject of long imagining. But a traveler arriving in the system would find 3 ordinary stars, of common and well-understood kinds, doing exactly what such stars do everywhere in the galaxy. The system is not strange. It is not exotic. It is, in every respect but one, an ordinary corner of the galaxy. Its single distinction is its nearness to us. And that distinction exists only because we are here to measure from. To anyone else in the galaxy, Alpha Centauri would simply be 3 more stars among the hundreds of billions. Its specialness, like the Sun's, is a matter of viewpoint rather than of substance. This is not a thought to be saddened by. It is, in its way, a gentle one. It means that the nearest star is not a rare prize, but a fair sample, that to know Alpha Centauri well would be to know something true about the ordinary furniture of the whole galaxy. The journey to the nearest star is a journey to a typical place, and the typicality is itself worth something. It means the galaxy is full of systems like this one, full of golden pairs and quiet red companions, and small rocky worlds in bands of twilight. Alpha Centauri is simply the one we can reach toward first. And there is a final detail in that backward view. Light carries the past. The sunlight that would reach a traveler 4 light years out left the Sun 4 years before it arrived. To look back toward home from the distance of Alpha Centauri is to see the Sun not as it is, but as it was. The same is true in the other direction. Every time we look at Alpha Centauri, we see it as it was 4 years ago. Across interstellar distances, every view is a view into the past, and the present, the shared single instant of now, is something no two stars can ever truly hold in common. There is one further feature of the journey worth describing before the destination resolves, and it concerns the direction of travel rather than the distance. Alpha Centauri lies in a particular part of the sky, in the southern heavens, in the region of the constellation that gives the system its name, the constellation of the Centaur. From the southern hemisphere of the Earth, the system is high and prominent. From the far north, it never rises at all. A traveler setting out for Alpha Centauri would be heading toward a fixed point in that southern sky, and for the whole of the long crossing, that point would barely seem to shift. The destination is so far away that even crossing trillions of kilometers toward it would change its apparent direction only slightly. The traveler would aim at a star and hold that aim, unwavering, for the whole of an immense journey. It is also worth noting what the traveler would not encounter. There would be no other stars to pass closely. The route between the Sun and Alpha Centauri does not run near any third star. The few other stars that lie in roughly that part of the sky are all far more distant, scattered across the deeper galaxy, none of them close enough to the path to be more than distant points of light. The crossing is genuinely solitary. It does not thread between stars. It runs through the open dark between two of them, with nothing nearer than the origin behind and the destination ahead. And the traveler would carry, the whole way, a slowly changing view of the heavens. Near the start, the constellations would look almost exactly as they do from Earth, because the modest distance covered would not be enough to shift the apparent positions of the distant stars. But as the journey lengthened, as light year after light year fell behind, the nearer stars would begin, very slowly, to slide against the more distant background. The closest stars shift the most, the farthest barely move at all. By the time a traveler stood at Alpha Centauri, the night sky would be recognizably the Earth sky, and yet subtly rearranged. The near stars nudged into slightly new positions, the constellations gently distorted, and the Sun itself added as a new point of light where, from Earth, there had been none. So the journey begins here, with the Sun fading behind and the emptiness opening ahead. 4 light years of near-perfect silence, with a small family of stars waiting at the far end. There are no way stations along the way, no landmarks, nothing to pass. There is only the slow crossing of a gap that light itself takes 4 years to bridge. And it is worth settling into that idea slowly, because the size of the gap is what makes Alpha Centauri what it is. It is close enough to be called a neighbor, and far enough to remain a world apart. The whole of the journey ahead lives in the space between those two truths. Part 2. The first sight of a triple star. After the long crossing, the destination begins to resolve. And here the journey delivers its first genuine surprise, because what looks from Earth like a single star is not a single star at all. On approach, that one brilliant point of light slowly separates, first into 2 and then into 3. Alpha Centauri is not a star. It is a system of stars, a small family bound together by gravity, with a structure and an internal life of its own. From the surface of the Earth, Alpha Centauri appears as one of the brightest stars in the southern sky, a single, steady point. To observers in the southern hemisphere, it is a familiar and prominent light, one of the brightest in the entire night. But the eye cannot divide it. The 2 bright stars at its heart are so close together as seen across 4 light years that they merge into one. Only a telescope, or the slow approach of a journey, reveals the truth. The system contains 3 stars, and they are not arranged in any simple way. two of those three stars form a close pair, orbiting each other at the center of the system. The third is a small, faint, red star, far outside the central pair, drifting at the very edge of the system's gravitational reach. So the structure has two distinct parts. There is a bright inner pair, and there is a dim, distant outlier. To understand Alpha Centauri is to understand both of those parts, and the great gulf of space that separates them. The two central stars are usually called Alpha Centauri A and Alpha Centauri B. Together, seen from a distance, they blend into a single golden point, which is the light we recognize from Earth. The third star is named Proxima Centauri. It is far too dim to be seen from Earth without a telescope, even though, of the three, it is the one that lies closest to us. This is the system's first lesson. The nearest star to the Sun is not one object. It is a household of three. The two central stars circle their common center of gravity over a period of roughly 80 years. It is worth being precise about what that means. Two stars bound by gravity do not have one orbiting the other, as a planet orbits a star. Instead, both stars orbit a shared point between them, the center of mass of the pair, each tracing its own ellipse around that invisible balance point. The more massive star traces a smaller path, the less massive one, a larger path, and the two move in step, always on opposite sides of the center, like two figures turning while holding hands. Their separation is not fixed. As they move along their orbits, the distance between them changes considerably. At their closest, the two stars draw as near to each other as the Sun is to the planet Saturn. At their farthest, they spread apart to a distance greater than that between the Sun and Neptune. The orbit is a stretched ellipse rather than a circle, and so the two stars are forever drawing together and easing apart, closer and then wider, in a cycle that takes a little less than a single human lifetime to complete. Neither star ever escapes the other. The bond is permanent, but the distance within that bond is always changing. Proxima Centauri, the third star, lies far beyond this central pair. The distance from Proxima to the two inner stars is roughly a fifth of a light year. To grasp how large that is, recall that the central pair, at their widest, are separated by only a few times the size of our planetary system. Proxima sits thousands of times farther out than that. The gulf between the bright pair and the faint red companion is not a small extension of the system. It is the overwhelming majority of the system's size. If the central pair were two coins held a hand's width apart, Proxima would be a third coin set down in another room entirely. It is bound to the central pair by gravity, but the bond is gentle, stretched across a gulf so wide that a single orbit of Proxima around the inner two stars takes something on the order of 500,000 years. 500,000 years is a span longer than the entire existence of our own species. Proxima has not completed even a small fraction of one circuit since the first humans looked up at the sky. Its orbit is so slow and so vast that across the whole of recorded history, it has barely seemed to move at all relative to the pair it circles. This vast, slow orbit is why there is a genuine question about how to think of Proxima at all. Is it a true member of the family, or a distant cousin that merely happens to be traveling alongside? For a long time, this was uncertain, because a bond so gentle is difficult to confirm. Careful measurement of the three stars' motions has now shown that Proxima is indeed gravitationally bound to the central pair. It belongs to the system, but it belongs to it the way a far outer moon belongs to a planet, held at the very edge of an influence that reaches just far enough to keep it, and no farther. Because Proxima sits slightly closer to the Sun than the central pair does, it currently holds a particular distinction. It is the single nearest star to our solar system. Of all the stars in the night sky, this small, faint red one is the closest to home. The distinction, though, is not permanent. The stars are all in motion, drifting slowly through the galaxy along their own separate paths. Over tens of thousands of years, that slow drift will eventually pass the title of nearest star to others. For now, and for a long while yet, it belongs to Proxima. It is worth being clear about how the distance to a star like Alpha Centauri is even known, because the answer is quietly elegant. The method relies on a simple effect that anyone can demonstrate. Hold up a finger at arm's length and look at it first with one eye and then the other. The finger appears to shift against the distant background. The nearer the finger, the larger the shift. Astronomers use exactly this effect, but with a far larger baseline. As the Earth travels around the Sun, our viewpoint shifts from one side of the orbit to the other. A nearby star, observed from those two opposite viewpoints, appears to shift very slightly against the far more distant background stars. The size of that shift reveals the distance. For Alpha Centauri, the nearest system, that shift is the largest of any star, and yet it is still tiny, a movement so small it requires careful and precise measurement to detect at all. That smallness, even for the very nearest star, is one more way of feeling the scale of interstellar distance. The closest star in the whole sky shifts against the background by an amount that the unaided eye could never notice. The distances are real, and they are measured, and the measuring itself is a quiet reminder of how far away even the nearest neighbor truly is. The arrangement of Alpha Centauri raises a broader point about stars in general, and it is a point worth pausing on, because it gently corrects an assumption most people carry without noticing. The Sun is a single star, traveling through the galaxy alone, with no stellar companion. It is easy to assume this is the normal condition for a star. It is not. A great many of the stars in the galaxy exist in pairs, in triples, or in larger groupings. Some systems hold 4 stars, or 5, or more, arranged in nested pairs and hierarchies. Single stars like the Sun are common, but they are far from being the universal rule. Stars in multiple systems are born together, from a single collapsing cloud of gas and dust. A cloud large enough to form a star is often large enough to fragment as it collapses, breaking into 2 or more dense knots, each of which becomes a star. Those sibling stars, born from the same cloud at nearly the same time, begin their lives close together, and gravity holds many of them together for the rest of their existence. A multiple star system is, in a real sense, a set of siblings that never parted. Alpha Centauri's 3 stars almost certainly formed this way, together, from one nursery of gas, and they have traveled through the galaxy as a family ever since. The 2 bright central stars and the faint red outlier share a common origin. They are the same age, made from the same material, set out from the same place. Seen in this light, Alpha Centauri is not only the nearest star system, it is also a glimpse of a more common kind of stellar household than our own. The Sun's solitude, which feels so natural to us, is not the galaxy's default. Many stars have company. Our own star is, in this one respect, the unusual one. Whether the Sun was always alone, or whether it too was born among siblings that have long since drifted away into the galaxy, is one of the quiet, open questions of our own origin. It is worth considering, too, how the 3 stars hold together at all, because a system of 3 bodies bound by gravity is not a simple or an automatically stable thing. If 3 stars of comparable distance were placed near one another and set loose, their mutual pulls would be chaotic, and in time, one of them would likely be flung away entirely. What makes Alpha Centauri stable is its particular arrangement. It is what astronomers call a hierarchical system. The two central stars form a tight pair, close together and tightly bound. And the third star, Proxima, orbits not one of them but the pair as a whole, treating the close inner two almost as if they were a single combined mass. This hierarchy is the key to the system's endurance. Because Proxima is so far from the central pair, it does not feel the two inner stars as separate, tugging objects. It feels them as one. The central pair, in turn, are bound so tightly to each other that Proxima's distant pull cannot disturb their dance. The system is, in effect, two simple two-body problems nested one inside the other, and two-body orbits are stable and predictable in a way that tangled three-body arrangements are not. Alpha Centauri has held this arrangement for billions of years, and it will hold it for billions more. The family is not a fragile one. There is a further consequence of this structure worth drawing out. The two central stars, being so close, share a great deal of their environment. They formed side by side, and they have aged side by side. Proxima, far out at the edge, has lived a more separate life, in its own quieter region of the system, far from the brightness of the inner pair. In a sense, the system contains two different neighborhoods. There is the bright, warm, crowded center, where two suns turn close around each other. And there is the dim, cold, spacious outer region, where a single small red star drifts almost alone. Both belong to Alpha Centauri. They are simply very different places within it. And so the first sight of the destination is the sight of a family. A bright golden pair turning around each other across 80 years, drawing close and easing apart in their slow elliptical dance. A faint red companion drifting far out in the dark, taking 500,000 years to complete a single loop. All three bound together in their patient hierarchical arrangement, all three carried along the same slow path through the galaxy, all three descended from the same vanished cloud of gas. The single point of light we see from Earth was always richer than it appeared. The journey has only made that richness visible. Part 3. Alpha Centauri A, the Sun's twin. The first of the three stars to examine closely is the brightest of them, Alpha Centauri A. It is the larger member of the central pair, and it is the one that holds a particular interest. Because of all the stars within reach of our own, it is the one most like the Sun. To arrive near Alpha Centauri A would be to arrive near a star that could almost be mistaken for home. Alpha Centauri A is a yellow star. It belongs to the same broad family of stars as the Sun, shines with the same warm color, and burns at very nearly the same temperature. Astronomers sort stars into classes by their color and their surface heat, a sequence running from hot blue-white stars through yellow and orange ones to cool red ones. The Sun sits in the yellow part of that sequence. Alpha Centauri A sits in the very same part, almost exactly beside the Sun. If you could place the two stars side by side, they would look like close relatives, the same color, the same character of light. Alpha Centauri A is slightly larger than the Sun and somewhat more luminous, pouring a little more light into space than our own star does. Its diameter is modestly greater. Its total output of light is noticeably higher. But the resemblance is genuine and deep, far deeper than the small differences. Astronomers describe it as a solar twin, and the description is not loose or poetic. It is a technical near match. Of all the stars in the Sun's neighborhood, Alpha Centauri A is the nearest thing to a second sun that exists anywhere within reach. The star's mass is a little greater than the sun's, and its surface glows at a temperature close to our own stars. It is also somewhat older than the sun, a mature, settled, middle-aged star. Astronomers can estimate the age of a star from a combination of its properties, and the estimates place Alpha Centauri A as a star that has been shining for several billion years, comfortably into the long and stable middle of its life. During this phase, which lasts for billions of years, a star like Alpha Centauri A does one thing steadily and well. It burns hydrogen in its core, and it shines. It is worth pausing on how that shining works, because the mechanism is the same one that powers the sun, and understanding it makes the star feel less like a symbol and more like a place. Deep in the core of Alpha Centauri A, the pressure and the temperature are extreme beyond ordinary description. The weight of the entire star presses inward on the core, and that crushing pressure drives the core's temperature to millions of degrees. Under those conditions, the nuclei of hydrogen atoms, which everywhere else in the universe repel one another, are forced together and made to fuse into helium. Each individual act of fusion releases a small amount of energy. A single one would be unnoticeable. But the core of a star performs this fusion on a scale beyond counting, an enormous number of fusions every second, continuously, for billions of years. The summed energy of all those countless small events is the light of the star. When sunlight, or the light of Alpha Centauri A, falls on a surface, it is carrying the released energy of hydrogen nuclei that were fused together deep in a stellar core. The light of a star is, quite literally, the energy of matter being transformed. That light does not escape quickly. Energy generated in the core of a sun-like star does not simply fly outward and into space. The interior of the star is so dense that a packet of energy released in the core is absorbed almost immediately by the surrounding material, then re-emitted, then absorbed again in an endless sequence of tiny steps. It works its way outward through the star's interior over an immense span of time, drifting and scattering, before it finally reaches the surface and streams free into space. The sunlight that warms a world is old light, generated long before it left the star. The same is true of every photon of Alpha Centauri A. Around a star of this kind lies a region astronomers call the habitable zone. It is the band of orbits where a world could hold liquid water on its surface, neither so close to the star that water boils away, nor so far that it freezes solid. Liquid water, as far as anyone knows, is closely tied to the possibility of life, and so the habitable zone is one of the first things astronomers consider when they study a star. Because Alpha Centauri A is brighter than the Sun, its habitable zone lies a little farther out than our own. A world that received Earth-like warmth from Alpha Centauri A would orbit at a greater distance than the Earth orbits the Sun, simply because the star it circled was pouring out more light. Such a world would have a longer year, tracing a wider path around a slightly brighter Sun. The habitable zone is not a guarantee of anything. It is only a statement about warmth, about the range of distances at which water, if a world had any, could remain liquid. A world in the habitable zone might still be a bare rock, or a world choked by a thick and crushing atmosphere, or a world with no water at all. The zone marks where conditions are not immediately hostile to liquid water. Everything else, the air, the water, the chemistry, the long quiet possibility of life, depends on the world itself and on a history that the zone alone cannot supply. Still, it is the natural place to begin looking, and around a sun-like star such as Alpha Centauri A, it is a comfortable and well-defined band. It is worth noting how steady a sun-like star is. because that steadiness matters for any world in the zone. Alpha Centauri A does not vary greatly in its output. It shines year after year and century after century with very nearly constant brightness. A world in its habitable zone would receive a dependable, even warmth, not a fluctuating or unreliable one. This constancy is one of the quiet virtues of a mature, middle-aged, sun-like star. It is not only warm at the right distance, it is reliably warm, and reliability across the long ages a world needs is itself a kind of gift. A star like Alpha Centauri A has a very long future ahead of it. It will continue to burn hydrogen steadily and to shine with its familiar yellow light for billions of years to come. The lifespan of a star is set chiefly by its mass, and a star of roughly the Sun's mass has a total hydrogen-burning life measured in the billions of years. Alpha Centauri A is partway through that life, with a vast stretch of stable shining still ahead. But no star burns forever, and the long life of a sun-like star does eventually reach its closing chapters. Those chapters are worth describing gently, because they are also the future of our own sun. When a star like Alpha Centauri A finally exhausts the hydrogen at its core, its structure begins to change. The core, no longer supported by the energy of fusion, contracts and heats. That contraction raises the temperature of the regions around the core enough that fusion begins there instead, in a shell surrounding the spent center. The added energy of that shell pushes the outer layers of the star outward, and the star responds by swelling enormously. As it expands, its surface cools, and its color shifts from yellow toward red. It becomes a red giant, a vast, distended star far larger than it is today, glowing with a cooler, redder light, large enough that it would engulf the inner orbits of its own planetary system. That swollen phase does not last, by the standards of a star's life. In time, the star gently sheds its outer layers, releasing them into space as an expanding shell of glowing gas, a soft and gradual loss rather than any violent event. The shed gas drifts outward and slowly disperses. For a while, that expanding shell glows softly, lit from within by the hot exposed core, forming one of the most delicate structures in the sky. Then the shell thins and fades into the surrounding dark, and its material mixes back into the interstellar medium, where, in time, it may become part of the raw material of new stars and new worlds. Nothing is lost. The matter of an old star returns, slowly, to the galaxy. What remains at the center is small and dense and quiet. It is the exposed core of the old star, an object called a white dwarf, roughly the size of a planet but holding a large fraction of the star's original mass packed into that tiny volume. The white dwarf no longer fuses anything. It simply radiates away its stored heat, glowing from warmth alone, cooling slowly across an immense stretch of time. A white dwarf does not end suddenly. It simply fades over a span of time so long that the universe is not yet old enough for any white dwarf to have fully cooled. The endings of stars like Alpha Centauri A are not abrupt. They are the slowest fadings imaginable, a gradual settling into quiet across spans of time the mind cannot hold. This is the fate that Alpha Centauri A shares with the Sun. The same kind of star lives the same kind of life, and comes, at last, to the same kind of long, quiet ending, the swelling into a red giant, the gentle shedding of the outer layers, the small, dense ember left behind to cool. To look at Alpha Centauri A is, in a real sense, to look at a preview of our own star's distant future. The two stars are walking the same path, a little out of step, and the elder of them shows the younger what is to come. It is worth dwelling a little longer on the resemblance between Alpha Centauri A and the Sun, because that resemblance is the reason the star matters so much to the human imagination. When astronomers search the galaxy for places that might support life, or for places that might one day receive travelers, they look first for stars like the Sun. The Sun is the one star we know to be hospitable, the one star with a living world, and so a star that closely matches it is naturally a star of interest. Alpha Centauri A is the closest such match there is. It is not a strange star, not a giant or a dwarf, or an unstable variable. It is a calm, ordinary, sun-like star, and it happens to be the nearest bright star to our own. A traveler arriving in the system would find Alpha Centauri A's light genuinely familiar in a way that is difficult to overstate. The color would be right. The warmth would be right. A world receiving the correct amount of that light at the correct distance would have skies and shadows and a quality of daylight that an earthly visitor would recognize at once. Among all the stars within reach, this is the one whose light would feel least like the light of an alien sun and most like the light of a second home. That familiarity is grounded in real physics rather than in sentiment. Two stars of nearly the same mass, the same composition, and the same age will behave in nearly the same way because the life of a star is governed by those few quantities. Alpha Centauri A matches the Sun closely in all of them. Its interior works the same way. Its surface behaves the same way. Its future will unfold the same way. The kinship is not a metaphor. It is a structural fact about two stars built to nearly the same design. But none of this is near. These changes lie billions of years ahead, far beyond any human horizon, far beyond the horizon of almost anything we can meaningfully imagine. For now, and for an immense span of time to come, Alpha Centauri A simply does what sun-like stars do. It shines, steadily and warmly, the familiar yellow light of a star that could almost be home, holding its place at the bright heart of the nearest system, turning its slow 80-year dance with its orange companion, pouring its light into the dark. Part 4. Alpha Centauri B, the orange companion. The second star of the central pair is a quieter and more modest star than its bright companion, but it is no less interesting, and in one particular respect, it may be even more so. Alpha Centauri B is the kind of star that astronomers regard as among the most promising places in the entire galaxy to search for other worlds. It is smaller than the Sun, cooler than the Sun, and dimmer than the Sun, and each of those qualities is, in its own way, an advantage. Alpha Centauri B is an orange star. On the sequence that sorts stars by color and heat, it sits one step below the Sun, in the orange band rather than the yellow. It shines with roughly half the light of the Sun, and its glow carries a softer, more amber tone than the white-gold light of its companion, Alpha Centauri A. If the two central stars were seen side by side, the contrast would be clear and quietly beautiful. One burns with a bright golden light. The other glows with a calmer, warmer, more orange one. They are a matched pair of unequal stars, and the difference between them is part of what makes the system worth describing. Despite being the fainter of the two central stars, Alpha Centauri B is in no sense a lesser object. It is a fully fledged star, substantial and stable, with a mass not far below the Sun's, fusing hydrogen in its core in exactly the way the Sun does. It simply does so at a gentler pace. And that gentler pace is the source of its most remarkable quality, which is time. Because Alpha Centauri B is less massive than the Sun, the pressure and temperature at its core are somewhat lower, and so it fuses its hydrogen more slowly. This is one of the deep and elegant rules of how stars work. A more massive star burns hotter and faster and dies young. A less massive star burns cooler and slower and lives long. Mass is the great clock of a star's life, and a smaller star is a slower clock. A smaller star is, in effect, a more frugal star. It draws on its fuel with greater patience, and that patience translates directly into lifespan. Where the Sun has a total hydrogen-burning life of roughly 10 billion years, an orange star, like Alpha Centauri B, can shine steadily for several times longer. Its life is measured in tens of billions of years, an expanse of time so long that it strains against comprehension. A star like Alpha Centauri B that is shining now will still be shining, with very little change, in a future so distant that the arrangement of the galaxy itself will have shifted, that constellations will have dissolved and reformed many times over. The orange companion is built for endurance. This long, stable life is a large part of why orange stars are valued in the search for life beyond the Earth. Life, as far as anyone can tell from the single example we have, is not a quick process. On the Earth, life appeared early but took an immense stretch of time to develop into anything complex. If a world is to develop a rich and complex biosphere, it may need an enormous, unhurried stretch of stable conditions in which to do so. A planet orbiting a star like Alpha Centauri B would have exactly that. The star would shine on it with a steady, patient warmth across a span of time far longer than the Sun can offer its own worlds. Time is one of the rarest and most valuable things a star can give to a planet, and the orange companion has time in abundance. There is a further reason orange stars are considered favorable, and it concerns temperament rather than lifespan. Orange stars of this kind tend to be stable in their behavior. They are not generally prone to the violent surface activity, the frequent powerful flares that trouble some smaller and cooler stars. Alpha Centauri B does its work quietly. It pours out a steady amber light, year after year, age after age, without the sudden outbursts that would make a nearby world a more difficult place. A world in a settled orbit around Alpha Centauri B would receive a calm and dependable source of warmth, a sun that could be relied upon. There is a way of placing Alpha Centauri B in the broader family of stars that makes its character clearer. Stars come in a great range, from brilliant, short-lived giants that blaze for only a few million years to the small, dim red dwarfs that endure for trillions. The Sun sits comfortably in the middle of that range. Alpha Centauri B sits just below the Sun, a step toward the long-lived, modest end. It is not a giant and not a dwarf. It is a solid, ordinary, lower-middle star, and stars of its kind are among the most numerous of the substantial, sun-like stars in the galaxy. There are a great many orange stars, like Alpha Centauri B, and each of them offers the same combination of steadiness and time. This is part of why the study of Alpha Centauri B carries weight beyond the system itself. It is not only the nearest example of an orange star. It is a nearby example of an extremely common kind of star, one that exists in enormous numbers across the galaxy. Whatever is learned about the worlds and the conditions around Alpha Centauri B is, in a small way, a lesson about a vast population of similar stars. The nearest orange star is a window onto a great many distant ones. So Alpha Centauri B is a star with a long future and a steady temperament. Whatever exists around it today, whatever worlds may circle it, would have an immense and unhurried stretch of time in which to continue existing, lit by a patient and dependable sun. The orange companion is patient in a way the sun is not, and that patience is its quiet gift to anything that might one day depend on it. The presence of two stars so near one another also shapes what the sky would look like from any world within the central pair, and this is one of the most evocative features of the entire system. From the surface of a planet orbiting either Alpha Centauri A or Alpha Centauri B, the other star would be a constant and remarkable feature of the heavens. It would not be a distant point of light lost among the others, the way a neighboring star is for us. It would be a brilliant body, far brighter than any planet appears in our own sky, a second source of light moving slowly against the background stars as the two suns circled each other. That movement would unfold across decades, not hours. Over the roughly 80-year cycle of the two stars' mutual orbit, the companion star would gradually change its position and its brightness, drawing nearer and growing more brilliant, then easing away and dimming again. The sky of such a world would keep a slow rhythm, a pattern of light that took a human lifetime to complete, rather than a single day. A person born on such a world might watch the companion star move through only a portion of its full cycle across their entire life. There would be no simple, repeating day and night of the kind the Earth knows. There would be a more complex pattern, a layered one. The local star would still rise and set, giving the world its ordinary day. But over and above that daily rhythm, there would be the slow, decades-long rhythm of the companion, brightening and dimming, near and far. The character of the nights would shift across the years. At certain points in the long cycle, when the companion star was near, it would be bright enough to cast faint shadows of its own and to light the night so that true and total darkness never came. The nights of that stretch of years would be soft, silver-lit nights, never fully dark. At other points in the cycle, when the companion was on the far side of its orbit, the nights would be darker, closer to the kind of night we know on Earth. A world of the central pair would not have a single fixed character of night at all. Its darkness would deepen and lift across the decades, following the slow dance of its two suns. The night of such a world would be a thing that changed across a lifetime, and an old inhabitant might remember the quality of the dark in their childhood as something different from the dark of their old age. There is a question that naturally arises about a world in such a system, and it concerns whether stable, temperate orbits can exist there at all. With two stars so close together, would a planet not be pulled and jostled until its orbit became unstable? The answer, worked out carefully, is reassuring. A planet orbiting close to just one of the two central stars, well inside the distance between them, would feel that star clearly as its sun and the other star only as a distant influence. Such an orbit can be perfectly stable across the long ages. There is room, around each of the two central stars, for a planet to circle quietly in a steady path. The two stars do not forbid worlds. They simply share the sky above them. This means the habitable zones of Alpha Centauri A and Alpha Centauri B are real regions, genuine bands of orbit where a temperate world could lie. Alpha Centauri B, being the dimmer of the two, has its habitable zone closer in, nearer to the star, because a world must sit closer to a fainter star to receive the same warmth. A temperate world of Alpha Centauri B would orbit at a modest distance, on a year shorter than the Earth's, lit by the calm amber light of its orange sun, with the brilliant golden companion moving through its sky on the long, decades-long cycle. It is also worth noting what such a world would not have. It would not have the violent flares that trouble worlds around the smallest red stars. Alpha Centauri B is stable. Its light is dependable. A world circling it would receive a steady warmth, undramatic and reliable, across an immense span of time. Of the 3 stars in the system, the orange companion may be, in this quiet way, the most welcoming. It offers light without violence and time without limit. This is worth letting settle slowly, because it is one of the most beautiful consequences of the system's structure. Imagine a world where the night itself keeps a rhythm measured in decades, where the sky holds 2 stars, one near and one far, one giving the day and one moving through the dark, where an object on the ground might, at certain seasons of the long cycle, cast 2 faint shadows at once. Alpha Centauri B, the quiet orange companion, is half of that arrangement. It is a gentle, patient, long-lived star, stable in its temperament and generous with time, and it is one of the 2 suns that would hang in the sky of any world fortunate enough to circle the heart of the nearest system. Part 5. Proxima Centauri, the faint red neighbor. Far from the bright central pair, out at the edge of the system's gravitational reach, lies the 3rd star. Proxima Centauri is the smallest and the faintest of the 3. It is so dim that it cannot be seen from Earth without a telescope. And yet, of all 3 stars in the system, it is the most important to us, for a reason that is almost absurdly simple. It is the closest. Of every star in the entire night sky, Proxima Centauri is the nearest to the Sun. Proxima is a red dwarf. This is the smallest and coolest kind of true star, far less massive than the Sun and far fainter. The category sits at the bottom of the sequence of stars, below the yellow stars like the Sun, and below the orange stars like Alpha Centauri B, down in the cool red end where stars are at their smallest and dimmest. A red dwarf is still a true star, fusing hydrogen in its core, but it is a star reduced to its most modest form. Red dwarfs are also, by a wide margin, the most common kind of star in the galaxy. The great majority of all the stars that exist are red dwarfs. If the galaxy's stars could be sorted and counted, the bright and famous ones, the brilliant blue-white giants, and the warm yellow suns would altogether be far outnumbered by the small, dim red ones. And yet not a single red dwarf can be seen from Earth with the unaided eye, because every one of them is simply too faint. The most abundant stars in the universe are also, to a human observer standing under a dark sky, completely invisible. The night sky we see is a deceptive sample. It shows us the rare bright stars and hides the common dim ones. Proxima Centauri holds only a small fraction of the Sun's mass, and it releases only a tiny fraction of the Sun's light. If Proxima were somehow placed where the Sun is, the daytime sky of the Earth would be dim and deeply red, lit by a star pouring out only a small fraction of the warmth and brightness we are used to. It is a modest star, by every measure of size and brightness, a small ember of a star compared to the bright furnace of the Sun. That faintness is the reason Proxima was discovered so late. Countless brighter stars, far more distant than Proxima, were catalogued and named and studied long before anyone identified the small red star that was, all along, our nearest neighbor. The bright stars announce themselves. The dim ones must be searched for. Proxima is the clearest possible demonstration that nearness and brightness are entirely different things. It is the closest star to the Sun, and it is also one that no one had ever noticed until astronomers learned to look carefully and systematically for dim things. Its name records its single most important property. The word Proxima means the nearest. It is, quite simply, the closest star there is. For all its faintness, Proxima Centauri has one quality that is genuinely staggering and that quality is endurance. Red dwarfs are the longest-lived stars in the entire universe. The same rule that governs all stars, that smaller means slower and longer-lived, reaches its furthest extreme in the red dwarfs. They burn their fuel so slowly, and they are able to draw on so much of their fuel so thoroughly that they can continue shining steadily for trillions of years. That figure deserves a moment of real attention because it is easy to read past it. The universe itself is currently something on the order of 14 billion years old. A red dwarf like Proxima can shine for a span hundreds of times longer than the entire present age of the universe. This means that no red dwarf anywhere has yet reached the end of its life. There has not been enough time. Every red dwarf that has ever formed is still shining, and will go on shining for an expanse of time so long that the universe, as it is now, is only the very first moment of it. This means that Proxima Centauri, despite being a star that has already existed for billions of years, has, in a real sense, barely begun. It will still be shining, still burning quietly and steadily, long after stars like the Sun and Alpha Centauri A have swelled into red giants, shed their layers, and faded to white dwarfs. It will shine on into a future so distant that there is almost no honest way to express it. A future in which the bright stars of today's sky are long extinguished, and the small red ones still hold their patient light. Proxima is a small, faint, patient star with an almost limitless expanse of time stretching ahead of it. But red dwarfs are not always calm, and here the portrait of Proxima gains its one note of restlessness. Many red dwarfs, and Proxima among them, are what astronomers call flare stars. They are capable of sudden, powerful outbursts. A flare is a brief, violent release of energy from the star's surface, an event in which the star can flare dramatically brighter for a short time, sending out a surge of light and of radiation. On a star as modest as Proxima, a flare can be a large event relative to the star's quiet, ordinary output, a sharp spike against an otherwise steady glow. These flares rise and fade over minutes to hours. They are driven by the star's magnetic activity, by the tangling and sudden release of magnetic energy near the surface. A small star like Proxima can be magnetically vigorous in a way that produces these frequent sharp outbursts. So the portrait of Proxima holds two things that seem opposed. Across the long view, it is the most patient star imaginable, steady for trillions of years. Across the short view, it is restless, capable of sudden sharp flares. Both are true. Proxima is patient and restless at once. This restlessness is one of the genuine complications in the question of whether worlds around such stars could support life. A planet orbiting close to Proxima would be bathed in the star's gentle, steady warmth for most of the time. But it would also be exposed, from time to these sudden outbursts of radiation. Whether a world could hold onto an atmosphere and shelter a surface beneath such a star across the long ages is an open and uncertain question. The flares are part of who Proxima is, and they are part of what makes its worlds a genuine mystery rather than a simple promise. It is worth holding the flares in proportion, though, rather than letting them dominate the picture. A flare is a brief event. Most of the time, across the great majority of its existence, Proxima simply shines, quiet and steady and deep red. The flares are punctuation, not the sentence. And whether they would actually prevent life on a nearby world depends on factors that are genuinely unknown, on whether a world has a thick atmosphere, on whether it has a magnetic field to deflect the worst of the radiation, on the chemistry of its air and the depth of any oceans. A flare-prone star makes the question harder. It does not answer it. The honest position is that worlds around red dwarfs are neither ruled out nor assured. They are simply, like so much about Alpha Centauri, an open and patient question. There is also a gentler way to think of the red dwarf's restlessness. It is the visible sign of a star that is thoroughly alive, churning all the way through, magnetically vigorous, working. A perfectly placid star would be a simpler star, but Proxima's flares are evidence of the same deep internal motion that lets it draw on all its fuel and last for trillions of years. The temper and the longevity come from one source. To watch a Proxima flare, if one could, would be to watch the surface expression of the very process that makes the star nearly immortal. Proxima's place in the system is the place of an outermost member. It orbits the central pair of bright stars at an enormous distance, far beyond them, and a single circuit of that immense orbit takes something on the order of 500,000 years. It moves at the very edge of the system's gravitational influence, the most distant and most loosely held of the three stars. Its bond to the central pair is real, confirmed by careful measurement, but it is gentle, stretched across a gulf thousands of times wider than our own entire planetary system. There is something worth saying about the structure of a red dwarf, because it explains both the long life and the restlessness. A red dwarf is small, and its interior is relatively cool compared to a larger star, and as a result, the whole body of the star churns and circulates. In a star like the Sun, only the outer layers churn in great rising and falling currents, while the deep interior is calmer. In a red dwarf, that churning reaches all the way through. The entire star is in slow, constant, overturning motion. This thorough churning has two consequences, and they pull in opposite directions. The first is the long life. Because the whole star circulates, fresh hydrogen fuel is continually carried down into the core, and the spent helium is mixed away. A red dwarf can therefore use almost all of its hydrogen, not merely the small central portion that a larger star consumes. It burns slowly, and it burns nearly completely, and that is why it lasts for trillions of years. The second consequence is the flares. The constant churning of the star's electrically charged material generates strong and tangled magnetic fields, and it is the sudden snapping and rearranging of those fields near the surface that produces the bright, sharp outbursts. The same restless motion that grants the red dwarf its long life also gives it its temper. So Proxima is a star defined by its smallness in nearly every respect. It is small and therefore dim. It is small and therefore long-lived. It is small and therefore fully churning, and therefore both magnetically restless and able to burn its fuel to the last. Every one of its defining qualities traces back to that single fact. It is a small star, the smallest kind of star there is, and it is our nearest neighbor among all the stars. There is a quiet lesson in Proxima's place at the bottom of the scale of stars, and it is worth drawing out before the journey moves on. The smallest stars are the most numerous, the longest lived, and the most patient, and yet they are the ones a person can never see. The sky we look up at is, in this sense, an unrepresentative sky. It shows the bright and the rare, the brilliant short-lived giants and the warm yellow stars, and it hides the small and the common and the enduring. If the night sky could be made to show every star at its true abundance, it would be transformed. It would be dominated, overwhelmingly, by small red points, the dim and patient majority, with the familiar bright stars scattered thinly among them. Proxima is one of that hidden majority, and it happens to be the very nearest of all the stars. There is something fitting in that. The closest star to the Sun is not a brilliant beacon. It is a modest red ember, of the most common and most overlooked kind, the sort of star that makes up the quiet bulk of the galaxy. Our nearest neighbor is an ordinary example of the galaxy's most ordinary kind of star. And it is exactly that ordinary, patient, long-lived little star that holds, in its faint warmth, the nearest world to our own. A red dwarf's longevity also means something for any world that circles it. A planet around Proxima would have, ahead of it, an almost limitless future of steady light. While a world around a sun-like star must one day face the swelling of its star into a red giant, a world around Proxima faces no such ending for an unimaginable span of time. The small red star will simply keep shining, gently and steadily, far into a future in which the brighter stars have all gone out. Whatever exists around Proxima has been given the longest lease the galaxy can offer. A faint red point, drifting far out beyond the brilliant golden pair, bound to them only just, taking 500,000 years to complete a single slow loop. That is Proxima Centauri's position in the family. And yet this small, dim, distant star is the one that matters most to the question this documentary is asking. Because Proxima is not alone out there. Proxima has worlds. And the nearest of those worlds is the closest planet to the Earth, anywhere beyond our own solar system. The faintest star in the system holds the nearest of all the worlds, and that is where the journey turns next. Part 6. The worlds of Alpha Centauri. A star system is most interesting, in the end, for what orbits it. The stars themselves are the engines and the anchors, the sources of light and the centers of gravity, but it is the worlds circling them that turn a system from a collection of lights into a collection of places. Alpha Centauri is now known to hold worlds. And the nearest of them, orbiting the faint red star Proxima Centauri, is the closest planet to the Earth, anywhere beyond our own solar system. That world is, by the standards of the great catalogue of known planets beyond the Sun, a modest one. Astronomers have now identified thousands of planets orbiting other stars, worlds of every kind, scorching gas giants and frozen rocky worlds, and planets unlike anything in our own system. Against that vast catalogue, the nearest world is not an extreme or a strange object. It is close to the size of the Earth, a rocky world rather than a giant of gas, the kind of small solid planet a person could, in principle, stand upon. Its single most extraordinary quality is simply its location. It is the nearest one. Of all the planets known to orbit other stars, this is the one closest to home. The world orbits very close to Proxima Centauri, far closer than the Earth orbits the Sun. In our own system, a planet that close to its star would be scorched beyond any habitability, its surface baked, any water long since boiled away. But Proxima is a faint star, pouring out only a small fraction of the Sun's light, and so the rules are different. That close orbit places the planet within Proxima's habitable zone, the band where the warmth received from the star is, in principle, right for liquid water to exist on a surface. The world is close to its star, and the star is dim. And the two facts together produce a planet that receives a temperate amount of light, neither scorched nor frozen. Because the planet orbits so close to Proxima, its year is extraordinarily short. The closer a world orbits its star, the faster it must move and the shorter its year. This planet completes a full circuit of Proxima in only a handful of Earth days. A creature standing on that world, if it measured time by the cycle of its planet around its sun, would count years that lasted barely longer than an earthly week. A human lifetime, lived there, would run to many thousands of such years. The world is also very likely tidally locked, and this is one of the most important facts about it. Tidal locking happens when a world orbits very close to its star for a very long time. The gravity of the nearby star raises a slight, permanent bulge in the body of the planet, and the pull on that bulge gradually slows the planet's rotation. Over a long span of time, the rotation slows until it matches the orbit, and the planet ends up keeping one face turned permanently toward the star, just as the Moon, locked to the Earth by the same process, keeps one face turned permanently toward us. If Proxima's world is tidally locked, as is very likely, then it has no ordinary cycle of day and night. One side of the world faces the star always, in perpetual day, the star fixed in its sky. The other side faces away always, in perpetual night, the star never rising at all. The day side would be the warmer hemisphere, continually lit and warmed. The night side would be the colder one, in permanent darkness. The world would be divided, permanently, into a lit half and a dark half. On a tidally locked world, the most temperate place would not be the continually heated day side or the deeply frozen night side, but the ring of land that lies between them. This is the terminator, the great circle of permanent twilight that separates the two hemispheres. Along that ring, the star would sit forever on the horizon, neither rising nor setting, casting a long, low, level, unchanging light. The terminator would be a band of endless dawn, or endless dusk, running all the way around the world, and if that planet holds any gentle and temperate place, it is most likely there, along the ring of twilight. There is one important softening to add to the picture of a tidally locked world, because the bare description of a baked day side and a frozen night side is not the whole story. If such a world holds a substantial atmosphere, that atmosphere would carry warmth. Air heated on the day side would flow toward the cold night side, and cold air would return, and across the whole world, the temperatures would even out, the extremes pulled gently toward a more uniform middle. An atmosphere is a great circulating blanket, and a world with one would not have a scorched half and a frozen half, so much as a warm side and a cool side, with the difference between them softened by the endless movement of the air. Likewise, if the world holds oceans, water too would carry and store and spread the warmth, smoothing the climate further. Whether Proxima's nearest world has such an atmosphere or such oceans is exactly the open question, and so its true climate cannot be stated. But it is important not to picture the world as more extreme than it need be. A tidally locked planet with a good atmosphere could be, across much of its surface, a temperate and gentle place. The fixed star and the unmoving light would make it strange. They would not, on their own, make it harsh. Whether the world holds an atmosphere at all is not known, and this is the honest center of the matter. The planet's closeness to a flare-prone star is a genuine complication. The flares of Proxima could, across the long ages, strip away a thin atmosphere, leaving the surface bare. Or a world with a sufficiently substantial atmosphere and a protecting magnetic field might endure them. The answer depends on conditions that have not yet been measured. It is important to be honest about this. The nearest known world is not a confirmed second Earth. It is a real, rocky, roughly Earth-sized planet, orbiting in the temperate zone of the nearest star. It is a genuine place and a genuine open question, and it is closer to us than any other world beyond the Sun's own family. Proxima Centauri may hold more than one world. Alongside the main confirmed planet, there are indications of at least one additional, smaller world, one that would orbit even closer to the star than the first, on an even shorter year. And there are fainter signs that hint at another, more distant planet, on a wider and slower orbit. These additional worlds are less certain than the main confirmed planet. They are signals still being tested, still being weighed against the difficulty of detecting small things around faint stars. But if they are real, then Proxima, the faintest star in the system, would hold a small planetary family of its own, a set of worlds circling a single dim red star out at the edge of the system. The picture here is deliberately incomplete, and it is worth being comfortable with that incompleteness rather than impatient with it. Detecting small planets around faint stars is delicate, painstaking work, drawn out over years of careful observation. The system around Proxima is still being slowly and patiently mapped, and the map is not finished, and may not be finished for a long time. What is known with confidence is that there is at least one world there, the nearest world of all, and that there may well be more. It is worth reflecting on what it means that planets around other stars are now found in such numbers at all. For most of human history, the planets of other stars were entirely a matter of speculation. No one knew whether the Sun's family of worlds was a common thing or a rare one. Then, within a span of only a few decades, the situation transformed completely. Planet after planet was found around star after star, until it became clear that planets are not rare at all. They are ordinary. Most stars, it now appears, host worlds of some kind. The galaxy is not a sparse place with a few scattered planetary systems. It is rich with them. Against that background, the worlds of Alpha Centauri are not a surprise. It would have been more surprising if the nearest star system held no planets at all. What makes Alpha Centauri's worlds special is not their existence, but their nearness. They are ordinary worlds, of the kind that fills the galaxy, and they happen to be the closest examples of that vast population. To study them is to study, in detail and at close range, what is almost certainly a common thing across the whole galaxy. The two central stars, Alpha Centauri A and Alpha Centauri B, are far more difficult places to search than Proxima, and the difficulty is instructive. The trouble is their brightness, and the fact that the two stars sit so close together in the sky. Their combined glare floods the region around them with light, and a faint planet is a small, dark thing trying to be noticed against that flood. A small, dim world, set against the brilliance of two suns, is close to the very limit of what current methods can detect. There have been tentative indications of a possible world in the habitable zone of one of the two central stars. It is a candidate, not a confirmation. It is the kind of faint signal that requires great care and great patience to test. The kind of result that may yet firm into a genuine planet, or may fade away as the observations improve. The honest summary is that the central pair is not yet known to host any confirmed world, but neither has the possibility been ruled out. The question stays open, and the search continues, year after careful year. It is worth understanding, briefly, how worlds around other stars are found at all, because the methods explain why Alpha Centauri's planets have been so slow and so difficult to reveal. Most known planets beyond the solar system are detected not by seeing them directly, but by their effect on the star they orbit. A planet's gravity does not only hold the planet in its orbit, it also tugs, very gently, back on the star. The star and its planet both orbit their shared center of mass, and so the star traces a tiny rhythmic wobble. Instruments sensitive enough to detect that wobble can reveal the presence of an unseen planet and even estimate its mass. A planet can also be found by a second method, when its orbit happens to carry it directly between its star and our line of sight. As the planet passes in front of the star, it blocks a minute fraction of the starlight, and the star appears to dim very slightly for the duration of the crossing. If this happens at regular intervals, the regular small dips reveal the planet's orbit, and, from the depth of the dip, its size. And a few planets, a small number, have been captured more directly still, seen as faint points of light beside the overwhelming glare of their star. This is the most difficult method of all, but it grows a little more possible with every improvement in the instruments. It is worth asking what the nearest world might actually be like as a place, while being careful to stay within what can honestly be said. A rocky planet close to the size of the Earth would have a solid surface. It would have a gravity not far from the Earth's, enough to hold a person to the ground in a familiar way, enough to hold an atmosphere if it had managed to keep one. It would have, somewhere on it, a range of temperatures, the warm day side and the cold night side, and the temperate ring between. These are not guesses. They follow from the planet's size and its orbit and the nature of its star. What cannot be said is whether it holds water, or air, or any gentleness of climate, or anything at all that lives. Those questions wait on observations not yet made. The world might be a bare rock, airless and still, its day side baked and its night side frozen hard. Or it might hold an atmosphere thick enough to carry warmth around from the day side to the night side, softening the whole world toward a single temperate state. It might have water locked as ice on the dark hemisphere, or pooled as liquid along the ring of twilight, or none at all. The honest position is one of open possibility. The nearest world is a real place whose character is genuinely unknown. That uncertainty is not a flaw in the story. It is the most truthful part of it. The nearest world beyond our solar system is close enough to point to and name, and still far enough that its surface is a mystery. It sits exactly at the edge of knowledge, a real planet that can be located precisely and described only in outline. It is, in the most literal sense, the nearest unknown. Each of these methods has played its part in what is known about Alpha Centauri. The system sits exactly at the frontier of these techniques. It is close enough that its worlds can be studied in a detail impossible for more distant systems, and yet challenging enough, especially in the glare of the bright central pair, that it still guards some of its secrets. Alpha Centauri holds worlds. At least one of them is the nearest world there is, a rocky planet in a band of twilight around a small red star. And the full census of that nearby family is still, quietly and patiently, being taken. Part 7. Standing on a world of Alpha Centauri. Having surveyed the 3 stars and the worlds known to orbit them, the journey turns to its most imaginative movement, though it is imagination grounded firmly in fact. The positions of the stars are known. Their brightnesses, their colors, their motions, the distances between them, all of these are known with real precision. From those known quantities, it is possible to describe, with genuine confidence, what the sky would actually look like from the surface of a world within this system. This is not invention. It is a view that follows directly and necessarily from the astronomy. Begin on the nearest of all those worlds, the rocky planet orbiting Proxima Centauri. Stand, in imagination, on its surface and look up. The local star, Proxima itself, would dominate the sky. Because the planet orbits so close to its small star, Proxima would appear far larger in that sky than the Sun appears from Earth. It would be a broad red disk rather than a small bright one, taking up a noticeably wider span of the heavens. But it would not be fierce or blinding. Its light is the light of a red dwarf, cool and deep and gentle. And the disk would glow with a calm, deep red rather than a piercing white. The light of a red dwarf is rich in red and in the infrared, the part of the spectrum that lies just beyond the reach of human eyes. A landscape lit by such a star would be a landscape of deep, warm, shadowed tones. The shadows would be long and soft. The colors would be muted and redshifted. It would have the quality of a perpetual late evening, the kind of light our own world knows only in the last hour before sunset, when everything is gold and amber and long shadow. Except that here, the light would never advance toward true night and never brighten toward a true noon. It would simply hold, steady and red, hour after hour, age after age, an eternal, held evening. And it would hold in a literal sense, because the world is tidally locked, and so the star does not move across its sky. On the day side of the planet, Proxima would hang motionless, fixed at whatever point of the sky it occupied, neither rising nor setting, neither climbing nor descending. There would be no dawn and no dusk, no progress of the star across the heavens, no change at all in its position. A person standing in one spot on the day side would see the star in exactly the same place every time they looked up, for the whole of their life. On the night side, the star would simply never appear at all. The sky there would be a permanent, unbroken dark. A world like this does not have days in any sense we would recognize. It has a lit hemisphere and a dark hemisphere, and a star that never moves. Far across that sky, whether the deep red of the day side or the darkness of the night side, two other stars would stand out with remarkable brightness. These would be Alpha Centauri A and Alpha Centauri B, the bright central pair, seen from the outer edge of the system, where Proxima drifts. From Proxima's great distance, the two bright stars would not be suns. They would be points of light. But they would be extraordinarily bright points, by a wide margin the most brilliant stars in that world's sky, a close golden pair shining far brighter than anything in our own night sky, bright enough to be unmistakable, bright enough to be the first thing the eye found in the dark. Those two distant stars would have a gentle and important consequence for the night side of Proxima's world. That dark hemisphere, turned forever away from its own red star, would not lie in total blackness. It would be lit, faintly, by the bright golden pair hanging in its sky. The night side of the nearest world would rest under a permanent dim twilight, never the full and absolute dark of a moonless night on a world with one sun, always touched by the light of the two distant companion stars. It is a strange and quiet image, and it is worth standing inside it for a long moment. A motionless red sun fixed in the sky. A world with no sunrise it will ever see. A band of endless level twilight encircling the planet from pole to pole. And in the permanent dark of the far hemisphere, two brilliant golden stars that never quite let the night become complete. It is worth lingering on that terminator, the ring of endless twilight, because it is the most habitable seeming part of the nearest world and the easiest to picture as a place. Along that ring, a traveler would stand with the deep red star resting permanently on the horizon, neither rising nor setting, casting a long, level light across the ground. Behind them, toward the night side, the land would slope away into deepening cold and dark. Ahead, toward the day side, it would brighten and warm. The ring itself would be the balance between the two, a band of perpetual evening encircling the whole planet, the same low red light falling at the same angle everywhere along it. A walk along that terminator would be a walk that never changed its light. There would be no morning ahead and no night behind, only the same held evening, mile after mile, all the way around the world and back to the starting point. It is a strange geography, with no east and no west in any meaningful sense, no progress of the sun to mark a direction. But it is not a hostile geography. The ring of twilight is, of all the regions of that world, the one where the temperatures would be gentlest, and the conditions least extreme. If the nearest world holds any place where a traveler could simply stand and rest, it is most likely there, in the long, quiet light of the endless evening. Now move inward, from the faint outer star to the bright pair at the heart of the system, and imagine standing instead on a world orbiting one of the two central stars, Alpha Centauri A or Alpha Centauri B. Here, the sky would hold two suns, and the experience of day and night would be richer and stranger than anything our own world offers. The local star, whichever of the pair the world circled, would provide the planet's day in the ordinary way, rising and setting, climbing and descending, marking out a normal cycle of light and dark. But the companion star would also be present in that sky, and it would not be an ordinary star. It would be a second brilliant body, moving slowly across the heavens on its own schedule, far brighter than any star or planet in the Earth's sky. It would not be a true second sun in the matter of warmth. It would lie too far from the world to contribute meaningfully to the planet's heat. But it would be dazzlingly, exceptionally bright, bright enough at times to cast a faint second set of shadows. An object on the surface of such a world might, at the right season, throw two shadows at once, one cast by the local sun and one by the brilliant companion, the two shadows falling at slightly different angles. The character of that companion's light would shift over the long decades of the two stars' mutual orbit. As the companion drew nearer along its 80-year cycle, it would brighten. As it eased away, it would dim. The nights of such a world would change across the years, in step with that cycle. When the companion star stood on the near side of its long orbit, the nights would never fully darken, lit always by that brilliant second star, soft and silver and never wholly black. When the companion swung to the far side of its orbit, the nights would deepen toward a truer darkness, closer to the night we know. A world of the central pair would keep a rhythm of night and day measured in decades, layered over the ordinary rhythm measured in hours, a sky of genuine and patient complexity, a sky that changed across a lifetime. The two suns would also rise and set on their own separate schedules, and so the days themselves would take on an unfamiliar character. There would be days when both suns were in the sky together, the world doubly lit. There would be days when one had set and the other still hung above the horizon, so that a kind of bright twilight took the place of true night, the second sun lingering after the first had gone. The pattern of light across such a world would not repeat in any simple daily way. It would weave together the fast rhythm of the local sun's rising and setting with the slow rhythm of the companion's decades-long orbit, producing a long, complex, never quite repeating sequence of brighter and dimmer hours. To live on such a world would be to live under a sky that rewarded attention, a sky whose state was never quite the same two cycles running. An inhabitant would learn the patterns of two suns, rather than one, would come to know the long seasons of the companion's approach and retreat. It is a richer sky than the Earth's, and a stranger one, and it is the natural sky of any world that circles one of the two bright stars at the heart of the nearest system. And from any of these worlds, from the nearest planet of Proxima, or from an imagined world of the central pair, there is one more sight to seek out, and it is the sight the whole journey has been quietly traveling toward. Turn the gaze back toward home. Our sun would still be visible from the Alpha Centauri system, easily and clearly visible. But it would not be anything special. It would not be the brightest thing in that sky. It would be an ordinary bright star, one good point of light among the many, sitting in the constellations of that system's night. Seen from the distance of Alpha Centauri, the sun would appear within a star pattern that we, on Earth, already know. It would fall within the familiar, W-shaped constellation that we call Cassiopeia, adding a single extra bright star to that well-known shape, quietly altering its outline. Anyone on a world of Alpha Centauri who learned the constellations of their sky would have, among them, a slightly changed Cassiopeia with one extra star. And that one extra star would be the Sun. Folded invisibly into that single unremarkable point of light would be the Earth and the Moon, and every planet of the solar system, and every ocean and mountain and city, and every life that has ever been lived, and every history that has ever unfolded. All of it, compressed by distance into one ordinary star in someone else's sky. It is worth pausing on what the night sky as a whole would look like from a world of Alpha Centauri, beyond the two suns and the single added star that is our home. The great majority of the night sky would be entirely familiar. The distant stars, the ones that make up the constellations, lie so far away that a shift of 4 light-years barely moves them at all. An inhabitant of a world in the Alpha Centauri system, looking up, would see almost exactly the constellations we see, the same broad patterns, the same distant bright stars, in nearly the same places. The deep sky is a shared sky. It is only the near things that are rearranged. The Milky Way itself, the soft band of light that is the combined glow of our galaxy's distant stars, would arch across the sky of an Alpha Centauri world, just as it arches across ours. The galaxy is so vast that moving 4 light-years within it changes the view of it not at all. Whatever worlds circle the nearest star, their nights are lit by the same galaxy, the same faint river of light that has watched over every night of human history. So the sky of an Alpha Centauri world would be a sky of mostly familiar things, with a few profound local differences. 2 suns instead of 1. A pattern of day and night unlike any the Earth knows. And, somewhere among the ordinary constellations, one extra modest star, easily overlooked, that happens to be the Sun, and to hold, folded invisibly within it, the whole of the world we know. There is a gentle symmetry here, and it is the still point that the whole journey has been turning toward. The nearest star is always someone's neighbor, and always someone's distant point of light, depending only on where the observer stands. To us, here, Alpha Centauri is the near and brilliant thing, the closest of all the stars, and the Sun is home, the center of everything. To an observer standing on a world of Alpha Centauri, it is exactly reversed. Their 3 stars are home, are the center of their sky and their warmth. And our Sun is merely the nearest star, a single bright point in their dark, the closest light in someone else's night. To travel to Alpha Centauri, in fact, or in imagination, is to arrive at a place from which home itself becomes a star. Part 8. The journey there and the long view. The final movement of this documentary steps back from the system itself. Having traveled to Alpha Centauri in imagination, having watched its single point of light divide into 3, having stood on its worlds and looked up at its strange skies and back toward our own Sun folded into Cassiopeia, it remains to ask the plain and practical question: could this journey ever be made, in fact? And then, having asked it honestly, to close with the long, quiet perspective that the whole journey has been building toward. Alpha Centauri is the nearest star system, and reaching it remains, for now, far beyond present ability. The obstacle is the one named at the very beginning of the journey. It is the distance. The gap is vast and empty, and entirely unforgiving of slow travel, and slow travel is the only kind currently within human reach. Consider what the journey would require at the speeds achievable today. The fastest spacecraft ever built have reached genuinely remarkable velocities. Some have used the gravity of the Sun and the planets swinging close past them to gain speed, building up to motions that would carry them across the whole of the inner solar system in a matter of weeks. And yet, even at those speeds, a probe sent toward Alpha Centauri would need tens of thousands of years to cross the gap. The fastest things we have ever launched, set on a course for the nearest star, would still take longer to arrive than the whole of human civilization has so far existed. A journey begun now, at the speeds we can now achieve, would arrive in a future so remote that the civilization that launched it might be unrecognizable, or transformed beyond knowing, or simply long gone. The craft would outlive its makers many times over before it ever reached its destination. It would arrive into a future that the people who built it could not imagine and would never see. This is the plain arithmetic of interstellar distance, and it cannot be argued with. To make the crossing within a single human lifetime would require something entirely different in kind. It would require speeds that are a substantial fraction of the speed of light itself, velocities far, far beyond anything that has ever been built, or that can currently be built, or that there is currently any practical means to build. Reaching such speeds is, at present, a problem without a solution. The energy required to push even a small craft to such a velocity is immense. The engineering to deliver that energy does not yet exist. By every honest measure, the nearest star, in human terms, remains profoundly far away. This is not a cause for disappointment, and the voice of this documentary does not treat it as one. It is simply the honest scale of the thing. Alpha Centauri is close only in comparison to the rest of the galaxy, where the distances between stars run to tens and hundreds and thousands of light years, where the nearest neighbor we have is, by the galaxy's standards, almost impossibly near. Measured against the galaxy, Alpha Centauri is our doorstep. Measured against a human life, it is far. Both things are true at once, and the truth of the distance is part of what makes the nearest star what it is. There is a way of holding the difficulty that turns it from a frustration into something closer to a calm. The vastness of the distance is not an accident or an obstacle placed deliberately in the way. It is simply how the universe is built. Stars are spread thinly through a galaxy that is mostly empty space, and that thin spreading is the same arrangement that gives each star its own quiet region, its own undisturbed neighborhood in which planets can form and settle into stable orbits. The emptiness that makes the journey long is the same emptiness that makes planetary systems possible. If stars were packed closely enough to visit easily, they would also be packed closely enough to disrupt one another's worlds. The distance is not the universe being unkind. It is the universe being spacious, and the spaciousness is part of what allows worlds to exist at all. So the difficulty of reaching Alpha Centauri can be set down gently rather than carried as a weight. The nearest star is far because the universe is large, and the largeness is not a flaw. It is the condition of everything. A galaxy crowded enough to cross easily would be a galaxy too turbulent to hold quiet worlds. The gulf between the Sun and Alpha Centauri is the same gulf in miniature that surrounds every star and shelters every planetary system, our own included. The dream of crossing that distance has, even so, produced a long and careful history of imaginative proposals. People have thought seriously, and for a long time, about how the journey to Alpha Centauri might one day be made. These ideas are not idle. They are careful attempts to reckon with the arithmetic of distance and to find, somewhere within the laws of nature, a way across. One family of ideas imagines very small and very light probes. Instead of a great ship, it proposes something tiny, a probe perhaps no larger than a small handmade object, light enough that it could be pushed to enormous speed by powerful beams of light directed at thin, reflective sails. Light itself carries a gentle pressure, and a sufficiently powerful beam striking a sufficiently light and reflective sail could, in principle, accelerate a tiny craft to a substantial fraction of the speed of light. Such probes, if they could ever be built and launched, might cross the gap not in tens of thousands of years, but in a matter of decades, arriving within a single human lifetime of their departure, sending back, after the long delay of the crossing and the 4-year delay of the light, the first close images of another star system. Another family of ideas imagines the opposite approach entirely. Instead of something tiny and fast, it imagines something enormous and slow. A great vessel, a self-contained and self-sustaining world, large enough to carry living travelers across the Gulf, but moving at the slower speeds we can more plausibly imagine reaching. Such a journey would take many human generations. The travelers who arrived would not be the travelers who departed. They would be the distant descendants, born along the way, of the ones who first set out, inheritors of a journey they did not begin, and a destination they had never seen, except as a point of light. Still, other ideas reach toward more advanced forms of propulsion, concepts that remain, for now, firmly in the realm of theory rather than engineering. There is also the patient possibility that the first knowledge of Alpha Centauri's worlds will come not from any journey at all, but from light. The instruments built to study other stars grow steadily more capable. With each new generation of them, fainter things become visible and finer details emerge. It is possible that, long before any craft could cross the gap, the worlds of Alpha Centauri will be studied closely from here, their atmospheres examined in the light that passes through them or reflects from them, their surfaces inferred from careful measurement. The first answer to the question of what awaits us at the nearest star may arrive not as a traveler's report, but as a pattern in starlight, read patiently across 4 light years. This is its own kind of journey, slower in one sense and faster in another. No craft moves, but the light has already made the crossing. The light leaving Proxima's world tonight will arrive here in 4 years, carrying within it whatever that world has to tell. To study that light carefully is to let the journey be made in reverse, the destination sending its news to us rather than us traveling to it. It is the gentlest form of exploration there is, and it may well be the first to bear fruit. None of the proposed journeys is close to being built. They are, at present, careful dreams rather than plans, sketches of what might one day be possible rather than blueprints of what will be done. But the fact that Alpha Centauri is the nearest star is what makes it the natural first destination of every such dream. If humanity, or its descendants, ever crosses the gap between the stars, this is the most likely first shore. It is the closest land on the far side of the interstellar sea, and so it is the place every dream of crossing returns to. And here the documentary turns, at the last, to the longest view of all. Alpha Centauri will not always be the nearest star. This is a fact easy to overlook, because on the scale of a human life, the stars seem perfectly fixed, an unchanging backdrop. But they are not fixed. They are all in motion, every one of them, drifting slowly through the galaxy along its own separate path, at its own speed, in its own direction. The patterns of the constellations are slowly dissolving and reforming. The neighborhood of the sun is slowly rearranging itself. Our own sun is moving, and Alpha Centauri is moving, and the distance between them is slowly, continuously changing. Proxima Centauri itself is, at present, very gradually approaching the sun. The whole Alpha Centauri system is drawing a little nearer. It will continue to close that distance over the coming tens of thousands of years, reaching its nearest point to the Sun in the deep future, when it will be somewhat closer than it is tonight. And then, having reached that closest approach, it will begin, just as gradually, to draw away again, receding slowly back into the depths of the galaxy. Even the nearest star is only passing by. The closeness this entire journey has been built upon is itself a temporary thing, a particular arrangement of a particular moment in the long, slow drift of the galaxy. On the timescale of the stars, our neighborhood is not a settled or a permanent place. It is a slow, drifting arrangement, endlessly and quietly rearranging itself across spans of time, far longer than any human history, far longer than the human story is ever likely to be. Stars approach and become for a while the nearest, and then drift on again, and others move into their place. Long before Proxima held the title of nearest star, others held it. Long after Proxima has drifted away, others will hold it in turn. Alpha Centauri holds it now. It has not always held it, and it will not hold it forever. There is a way of feeling this that is calming rather than unsettling. The drift of the stars is unimaginably slow. The rearrangement of the neighborhood plays out across hundreds of thousands and millions of years. On any scale a human being can feel, the stars are perfectly fixed, the constellations perfectly steady, Alpha Centauri perfectly and reliably the nearest star. The slow motion is real, but it is so gentle that across every night a person will ever look up. Across the whole of any life, the sky holds still. The drift is a truth for the deep ages. For the span of a human life, and for the span of all of human history together, the nearest star simply stays where it is. So the long view and the near view do not contradict each other. Across the deep ages, the neighborhood rearranges, and the title of nearest star passes quietly from one to another. Across a human lifetime, the sky is a fixed and faithful thing, and Alpha Centauri is, simply and dependably, the closest star there is. Both are true. The one is the slow truth of the galaxy, and the other is the steady truth of the night above any single life. And yet, for now, for the whole span of recorded human history, and for a long while still to come, Alpha Centauri is our nearest neighbor, and that is no small thing. 3 stars, bound together by gravity into a single family. A bright golden pair, turning around each other across 80 years, drawing close and easing apart in their slow elliptical dance. A faint, red companion, drifting far out at the edge of the system, patient beyond imagining, restless with its sudden flares. At least one rocky world, roughly the size of the Earth, circling that red star in a band of endless level twilight. All of it, a little over 4 light-years away. The closest other place there is. That is the quiet gift of the nearest star, and it is the thought to rest on as this journey comes to its end. Alpha Centauri is far enough away to remain a mystery. It still guards worlds we have not confirmed, atmospheres we have not measured, skies we have only imagined from the known positions of its stars. And it is close enough, at the same time, to remain a neighbor, a real and specific destination, holding real and specific worlds, waiting in the dark at the very edge of what we can almost reach. It has waited there, turning quietly, for billions of years. It is waiting there still, tonight, as it always has. And there is comfort in simply knowing it is there. A person does not have to travel to the nearest star to feel its nearness. It is enough to know that, 4 light-years away, in the southern sky, 3 stars are turning together in the dark. A golden one and an orange one, drawing close and easing apart across their slow 80-year dance. A small red one drifting far out beyond them, patient beyond all measure. And a rocky world, roughly the size of the Earth, holding to its band of endless twilight lit by a sun that never moves. All of it real. All of it there, right now, whether or not anyone is looking. The nearest star is not a story or a hope. It is a place, and it is genuinely close, as closeness is measured among the stars. To know that is its own kind of quiet companionship across the dark. The night sky is not only distance and emptiness. It also holds, near at hand, a neighbor, a small family of stars, and at least one world, waiting where they have always waited. We may never reach them, but they are there, and their nearness is real, and on any night, the thought of them can be a settling one. The nearest star asks nothing. It only keeps its place in the dark, and turns, and waits. And so we leave the three stars where they have always been, turning slowly together in the dark, 4 light years from here, holding their small rocky world in a band of endless twilight. The nearest star asks nothing of us. It simply waits, as it has waited for billions of years, for anyone willing to look its way. Let your breathing slow. Let the day drift far behind you. Sleep well, and good night.